Last 3 lectures we have been discussing about modal analysis of continuous systems. Now, we have solved the problem of modal analysis, which is nothing but solving an eigenvalue problem, as we have seen, analytically, which means that we are exactly solving the natural frequencies and the modes of vibration, which are characterized by the eigenfunctions. Now, doing an analytical solution is always preferable, because you can find out the effects of various parameters of the system on the modes of vibration and the modal frequency, etc. So, analytical solution is always preferable. However, we have seen that even in very simple systems, the solution of the modal analysis problem requires solving transcendental equations, possibly which might be quite cumbersome even numerically. So, in general, analytical solutions, though preferable, are sometimes cumbersome and computation intensive. So, it is of interest to know if numerical methods of modal analysis or approximate methods of modal analysis are possible. So, in this lecture and the next lecture, we are going to look at a few techniques for solving the modal analysis problem or the eigenvalue problem approximately numerically. So, what is our motivation for studying the approximate solutions? So, the first motivation is that the analytical solutions may be cumbersome. The other thing is, an approximate method can provide a quick solution to the modal analysis problem, which may be sufficiently accurate for our purposes. So, let us look at the methods that are available to us for approximate modal analysis. So, we are going to discuss in this course two methods, two broad methods, which are the energy based methods, which will be the topic of discussion in today's lecture, and in the next lecture we are going to look at projection methods. So, as the name suggests, this energy based methods will use the kinetic and potential energy of the system to determine the modes of vibration or the natural frequencies, while the projection method, as we will see very soon, they use the governing equation of motion directly to solve the modal analysis problem. So, the first method that we are going to look at is the Rayleigh method. So, this Rayleigh method is typically used to determine the fundamental frequency of a continuous system. And this method is used for conservative systems. So, we use Rayleigh method for conservative systems. So, how does this method work? So, let us understand this with the example of a bar. So, let us consider a tapered bar in axial vibration. So, we write the kinetic energy as 1/2 the density of the material times the area of cross section times an elemental length times the velocity square. Now, this integrated over the domain of the bar. So, that is the kinetic energy. The potential energy is 1/2 the Young's modulus times the spatial derivative of the field variable square dx and integrated over the domain of the bar. Now, this system, this bar in axial vibration, as we know, is a conservative system, which means that the total energy of this bar is a constant. So, the total mechanical energy this is a constant. Now, let us suppose that this system is vibrating in one of its modes. So, as we have already discussed that when a system is vibrating in one of its modes, the field variable can be written as a separable function of space and time in this form. So, this special solution form is valid for a system, for this bar vibrating in one of its modes. Now, we will substitute this expression in the total energy of the bar, and once we do that, what we obtain So, this is the expression of the total energy after we substitute this solution structure in the total energy expression. Now, if this total mechanical energy is to be a constant, then what it would require is that it should be independent of time, and this is possible only when the coefficient of sin square omega t and cos square omega t, they are the same, which means so energy is constant would imply these two, the coefficients of the sin square omega t and cos square omega t, they must be equal. So, therefore, we obtain this ratio, which is defined as the Rayleigh quotient. And this Rayleigh quotient is the key concept in Rayleigh's method. So, what we have done is we have considered the modal solution, substituted it in the total energy expression, total mechanical energy expression, and finally, we force the energy to be independent of time by matching the two coefficients of the sin square and the cos square omega t terms to obtain omega square as a ratio, which is known as the Rayleigh quotient. Now, sometimes this Rayleigh quotient is also expressed as maximum potential energy divided by the maximum kinetic energy. So, the amplitude, so the maximum potential energy would be the amplitude of the maximum potential energy would be the amplitude of the cosine square omega t term, whereas the maximum kinetic energy would be the coefficient of the sine square omega t term, and of course, this omega is solved in terms of this. So, this is 1. So, from here we solve for omega square as we have done here. Now, this in this Rayleigh quotient, if you know the exact eigenfunction, so if you substitute where I am using this exact superscript to indicate that u exact is the exact eigenfunction for a particular mode. In that case, if you put this in the Rayleigh quotient, what we will get is the exact circular eigenfrequency corresponding to that mode. But the problem comes because we do not know the exact eigenfunction. So, in that case, how do we use this Rayleigh quotient? So, usually what is done is we try to minimize this Rayleigh quotient. So, and by minimizing the Rayleigh quotient, we obtain the fundamental frequency. So, the fundamental frequency square is obtained by minimizing the Rayleigh quotient over a space of possible eigenfunctions u of x. Now, there is a restriction on how you can choose u of x in this minimization problem. The restriction is u must be from a member of the set of what are known as admissible functions. So, this u is a set of admissible functions. So, you must choose the possible eigenfunction from this set of admissible functions. Now, what are admissible functions? This we will come to very soon. So, let me write for this problem so the fundamental frequency squared is minimization over the set of admissible functions of the Rayleigh quotient. Now, we come to this admissible functions. So, what are admissible functions? These are functions which satisfy the following two properties. The first property is it is differentiable at least So, these functions are differentiable at least up to the highest order of spatial derivative in the energy expression. So, of course, these functions are spatial functions, and so they must be differentiable at least up to the highest order of space derivative or spatial derivative in the energy expression. So, in this example, for example, in this example that we are considering, the highest order of space derivative is 1. So, the set of admissible functions should be differentiable up to first order. The second important property that it should satisfy is that it should satisfy all the geometric boundary conditions of the problem. So, admissible functions must satisfy all the geometric or essential boundary conditions of the problem. So, they satisfy all the geometric or essential boundary conditions of the problem. So, these two properties, the functions that satisfy these two properties are known as admissible functions. Now, such functions can be constructed using polynomials trigonometric functions and other such elementary functions. Now, let us look at this example of the tapered bar. So, as you can see, it is fixed at x equal to 0 and it is free at x equal to L. So, the geometric or essential boundary condition is on the left boundary where the bar is fixed. So, we must choose functions, admissible functions which satisfy the boundary condition at the left. So, let us look at such functions. So, we must have So, we have to choose admissible functions for this problem such that it is 0 at x equal to 0. This is the minimum condition that is required. So, a possible choice we may write it like this, x over L, but we can have a class of these functions by raising it to a power alpha. So, we actually have functions which, depending on alpha, for example, if alpha is 1, then this is linear. For other powers, it can go like this or it can go like this. Now, so this alpha we will initially keep it arbitrary, and we are going to substitute this in the Rayleigh quotient, and we are going to look at what is the Rayleigh quotient with this expression of admissible function. Now, one thing that you can see that we now have not one function, but we have a class of functions, and we can adjust alpha and see which function minimizes the Rayleigh quotient. So, this alpha provides us with a handle to solve a minimization problem as we have formulated it. So, if you calculate the Rayleigh quotient with this admissible function, then the Rayleigh quotient finally turns out to be a function of alpha, which is unknown as yet, and this expression turns out to be, this can be solved very easily, and what we obtain is this expression of the Rayleigh quotient. Now, so this term is the I mean has the properties of the bar, the geometric as well as material properties of the bar, while this coefficient, which is a function of alpha, determines the Rayleigh quotient. Now, this alpha is unknown as yet. So, we can put various values of alpha, or we can minimize the Rayleigh quotient with respect to alpha and determine alpha. So, let us see what happens if alpha is 1, and this remember is omega square. So, this turns out to be 70 over 16. So, this is an estimate of omega really the fundamental circular frequency, and this turns out to be 1. Now, let us see what happens if we minimize with respect to alpha. So, which means if you do this minimization, this gives and corresponding to this So, you see that this value is lower than this. So, this is a better estimate of the circular natural frequency. Now, we have solved this problem of the tapered bar in a previous lecture analytically, and the exact circular natural frequency that we determined was this. So, this is still lower, as you can see that this is higher than the exact, but they are quite close. This is within 3% of the exact. So, we have fairly accurately estimated the fundamental frequency of a tapered bar using a very simple method. But this, of course, this gives the best estimate based on the form of or structure of admissible function that we have chosen. But remember that when we go on to calculate stress, since this alpha is less than 1 for our best estimate, the stress that we will calculate at x equal to 0 will be infinite. So, it will have some, it will give some unrealistic estimates of stress in the bar. However, the frequency estimate is fairly accurate. Now, here using Rayleigh method we have estimated the fundamental frequency. Now, can we now go on to find out the higher frequencies? Now, that is possible using what is known as the Rayleigh-Ritz method. So, what we additionally have in this method is the Ritz expansion. So, we make use of the Ritz expansion of the amplitude function in the Rayleigh quotient. So, what I mean, so if you see this Rayleigh quotient, let us say for our problem of the tapered bar, so we will minimize this and u has to be chosen from the set of admissible functions. Now, this u, the amplitude function, we will expand I will put a tilde symbol to distinguish this function from the basis functions that we are using. So, like in the previous example, in the Rayleigh's method we had kept an unknown parameter alpha. Here we will expand the amplitude function in terms of admissible basis functions and certain unknown coefficients alpha. So, this is a linear combination of these basis functions, admissible functions. So, these are all admissible functions. And we can take any number of terms. Now, when we substitute this kind of an expansion, the Rayleigh quotient can be written as, so this I can write as a vector multiplication. So, alpha is a column vector and u is also a column vector. So, the dot product will represent this scalar function u tilde, and when I substitute this expression in the Rayleigh quotient, I can write in this form, where K, the matrix K, so the ijth element is expressed in this form, and similarly for the ijth element of this matrix M, is expressed in this form. Now these remember this alpha vector is unknown. So, we have to minimize with respect to this vector alpha. So, which implies that now this Rayleigh quotient is a function of this vector alpha, and this must be put to 0. So, the derivative must vanish for extremization. Now, this derivative implies that this derivative has to be taken with each element of this vector alpha. So, we have, if there are capital N elements in this vector alpha, then there will be n equations in n unknowns. So, if you consider this expression of the Rayleigh quotient, and if you perform this derivative, which is straightforward, finally, what you will arrive at now, here how will omega enter? We have used this expression here. So, if you perform the derivative, this coefficient actually turns out to be this ratio, which I am replacing by omega square. Now, this is a discrete eigenvalue problem. Which can be solved very easily to determine omega and this vector alpha, the eigenvectors alpha, and finally, once we have the circular eigenfrequencies and the corresponding vectors alpha I, these can be used to determine the corresponding eigenfunctions. using those basis functions, basis function vectors, vector u. So, using Rayleigh-Ritz method, we can find out not only the fundamental, but higher modes of vibration. Now, as a thumb rule, if we want, because the accuracy of these various modes will be different. So, as a rule of thumb, if we want n modes accurately, we must take 2n terms in the expansion. I mean, this is a rough estimate, rough way of estimating how many terms you must have in the expansion, and this may or may not work always, but this is a good way to start. So, if you want n modes accurately, reasonably accurately, then you must have double the number of terms in your expansion. Now, there exists another method which is quite powerful in this class of methods, which is known as the Ritz method. Now, in the Ritz method, we use the idea of Ritz expansion of the field variable and substitute this expansion directly in the variational formulation. So, this method works with a variational formulation of dynamics. So, let us see for once again for the tapered bar, we know that the variational formulation for this tapered bar reads now here we use this expansion again in terms of admissible functions. Now, once you substitute this in the variational form, in the variational formulation, and simplify. We obtain this, where well this integration over the space has already been performed. So, we substitute this here, and since these functions, admissible functions, are known, this basis is known to us, we can perform this spatial integration and obtain this variation of this discretized problem. So, here this matrices M and K are given by this expression, and we know that, and this is now the Lagrangian of a discretized system, and the equations of motion can be immediately written So, in this Ritz method we have essentially discretized our problem. Now, once we have discretized, we can search for solutions as we do for discrete systems. So, we search for modal solutions of this form and we solve the eigenvalue problem. So, after this the things are very standard. So, let us look at the axial vibrations of the tapered bar once again. So, here I have written out the admissible functions that we have chosen. So, h of x for j 1 and 2 we have, so we have taken two functions and discretized using these two functions. The equation, the discretized equation of motion is shown below. So, once you have the discretized equations of motion, then the standard procedure follows, which means that you assume a solution structure as shown here, you come to the eigenvalue problem and finally the characteristic equation. Now, if you solve this characteristic equation, you will obtain the eigen frequencies of the system. Now, solving this, we obtain the circular eigen frequencies. As you can see, omega 1 superscript capital R is calculated using the Ritz method, and similarly omega 2 superscript capital R, and they are compared with the exact circular eigen frequencies. And you can see that the fundamental, we have taken two terms, and the fundamental is fundamental frequency, circular frequency is matches quite well with the exact, while there is some error in the second circular natural frequency. Now, this Ritz method and even Rayleigh's method, it has an upper bound property. Which means that the natural frequency calculated from these approximate methods is always greater than the exact, which means that this gives an upper bound. The actual natural frequency the actual natural frequency of the system is lower than what you calculate using these approximate methods. Now, here you can see the eigenvectors k1 and k2 and the corresponding eigenfrequencies that have been determined by using the Ritz method. And once you plot these eigen functions, so this shows the comparison of the eigenfunctions calculated by the Ritz method and those obtained from the exact solution that we had discussed previously. So, again you can see that the fundamental eigenfrequency matches quite well with the exact, while that of the second mode is in error, especially at x over L equal to 1, since we are considering only admissible functions which satisfy the geometric boundary condition, which is at x equal to 0, while the natural boundary condition is not satisfied with 2 terms. You have to take more and more terms, and then there is a convergence to the exact solution. Now, we will summarize this lecture. So, we have considered approximate modal analysis based on energy methods, which uses admissible functions. We have looked at 3 methods: Rayleigh quotient, Rayleigh-Ritz method and Ritz method, and these methods have an upper bound property of the eigenvalue estimates, and these methods work for conservative systems with potential forces. With that, we conclude this lecture.